So remember that a lot of the concepts that we've learned in this class are concepts that can be defined purely in terms of addition and scalar multiplication. These include the concepts of span, linear independence, and basis. So in this lecture, we're going to go through these concepts again, understand what they mean in terms of general vector spaces, and just see some examples in vector spaces that are different from Rn. So let's start with span. And actually, there's two different ways that the word span is used, and so we'll go through each of those separately. So the first is that span can be used as a noun, where if you have a set of elements in a vector space, then you can take the span of those elements, which is defined as the set of all linear combinations of those elements. And then by exactly the same argument that we made when doing this for Rn, you can show that a span of a set of vectors is a subspace of the vector space. But the word span can also be used as a verb, but it's very closely related. The idea is that if the span of v1 to vm is equal to the whole vector space V, then we can say that these vectors span V. So in other words, the vectors v1 to vm span V if every element of V can be expressed as a linear combination of the v1 to vm. All right, so the next thing is linear independence. So the intuitive idea of linear independence is that you have a set of vectors which aren't redundant in any way. And that means that none of the vectors are zero, and none of them can be expressed as a linear combination of the others. But if you remember when we first encountered linear independence with vectors in Rn, we proved that there was this equivalent condition that the only solution to the homogeneous equation, where you're writing 0 as a linear combination of the vectors, that the only way to do that is with the trivial solution, where all of the coefficients are equal to 0. Now, if you go back and look at that proof, you'll notice that the proof only used algebra that involved addition and scalar multiplication. There was nothing else that happened there. So that proof works equally well with vectors in an arbitrary vector space. And so in practice, this is going to be the condition that you'll use to check whether a set of vectors is linearly independent. And then finally, we have the concept of basis. So a set of vectors is a basis for V if they span V and are linearly independent. So intuitively, this means that there's enough vectors that you can produce every vector in V as a linear combination of these vectors. But on the other hand, there aren't any vectors that are unnecessary or redundant. And so intuitively, I would say that a basis is a set of vectors that perfectly describes the vector space. Okay, so let's look at a couple of simple examples. So remember that Pn is the space of polynomials of order less than or equal to n. A convenient basis for Pn is just the set of powers of t that go all the way up to t to the n, including t to the 0, which is 1. And I think this is something where you don't even have to write down equations to check it, because the way that you actually write down elements of Pn is as linear combinations of these things. And as another example, we can consider the space of 2 by 2 matrices, and a good basis for that would be the 4 matrices where you have a 1 in one of the entries and zeros in all 3 of the other entries. Again, it's pretty clear that every 2 by 2 matrix can be written as a linear combination of these, and none of these can be written as linear combinations of the others. Okay, so we'll see some more interesting examples later, but for now it's probably good for you to just feel like you understand these basics. So remember that we used the concept of basis to define the dimension of a subspace. So now we can do the same thing, but in this general context of vector spaces. So if a vector space V has a basis with n elements, then we'll say that the dimension of V is n. And then the notation for that is dim of V equals n. So the first concern that you'd have about a definition like this is it well defined? And this is something that actually came up earlier when we were talking about definition. Is it possible that you have two different bases for the same vector space that have different numbers of elements? And the answer is no. If you have two different bases for the same vector space, then they're going to have the same number of elements. And this is a theorem that we have to prove. So I'll go through the proof now, but I'll warn you that it's a little bit technical and it's not that big of a deal if you don't get everything. So the first point is that since v1 to vn is a basis, we can write any vector in V as a linear combination of those vectors. And so in particular, we can write these W vectors as a linear combination. So we could write W1 as A11 times V1 up to A1n times Vn, and then we can do the same thing for all of the other W vectors. And now you'll notice, if you look at these equations, there's a little array of coefficients that appears there. And so we'll actually write down a matrix where every column of the matrix consists of the coefficients that appears in each of the equations that we just wrote down. There's a sense in which this is the matrix that changes basis from the V basis to the W basis, but we'll talk about that later. For now, the key thing to remember is that each column of this matrix represents the W vectors in terms of the V vectors. And so then, because this set of W vectors is linearly independent, the reduced echelon form of this matrix will have a pivot in every column, because that's what happens when the columns of a matrix are linearly independent. I know that I'm doing a lot of steps at once here so I can fit this proof on a slide, so don't worry too much if you don't understand every detail there. But the key point is that if there's a pivot in every column, that can only happen when the number of columns is less than or equal to the number of rows. And that's just because you can't have more than one pivot in a row. So if you have a pivot in every column, there has to be at least one row to go along with each of those columns. And so anyway, in this case, the number of columns is m and the number of rows is n. And so we have deduced that m is less than or equal to n. But we could actually make the same argument, swapping the v's and the w's, and we would conclude that n is less than or equal to m. And then the only way m can be less than or equal to n and n is less than or equal to m would be if the two numbers are equal, if m is equal to n. And that's the proof. All right, so let's look at a few examples. So remember we said that a basis for Pn just has all of the powers of t starting from t to the 0 and going all the way up to t to the n. So there's n plus 1 things on that list. And that means that the dimension of Pn is n plus 1. So then also recall that a basis for the space of 2 by 2 matrices consisted of these 4 matrices with 1s in one entry and 0s everywhere else. And since there are 4 basis elements, this means that the dimension is 4. And I think once you understand that example, then you can see how more generally the space of m by n matrices would be m times n dimensional. Okay, but these examples might feel like they're a little bit too simple, and so I'll give you a more interesting example that actually combines a lot of the things that we've been learning recently. So let's say that W is the set of polynomials in P3 such that P prime of 1 is equal to P of 3. We'll show that W is a subspace of P3, and then we'll find a basis, and then in finding a basis, we'll know what the dimension is. Okay, so first let's check it's a subspace. And the first thing we want to check is the 0 vector in there? The 0 vector in P3 is the polynomial whose formula is P of t is equal to 0. So it's 0 for all t. Well, if you take the derivative of 0, it's still 0, and if you plug in 1 into that, it's still 0. And similarly, if you plug in 3 into 0, you get 0. So P prime of 1 is equal to 0 in this case, and P of 3 is equal to 0 in this case. And those two things are equal to each other. And so yes, it's in W. Okay, so the next thing we want to check is that if you have two things in W and add them together, you get something that's in W again. So suppose that P of t and Q of t are in W. Then that means that they satisfy the condition P prime of 1 is equal to P of 3 and Q prime of 1 is equal to Q of 3. And the question is, does their sum satisfy that condition? So we want to check whether P plus Q prime of 1 is equal to P plus Q of 3. So I have a little question mark there because we don't know for sure that that's true yet. But we know that the left-hand side is P prime of 1 plus Q prime of 1, and we know that the right-hand side is P of 3 plus Q of 3. And now we can see that those things have to be true because we already know that P prime of 1 is equal to P of 3 and Q prime of 1 is equal to Q of 3. And then the third thing you would want to check is the scalar multiplication compatibility, which is a similar sort of argument to what we just did here, and so I'll leave that for you to do. But now the question is, how do we find a basis for this subspace? And the way to do that is that you turn it into a system of equations. So what you do is you start by writing P of t as a naught plus a1 times t plus a2 times t squared plus a3 times t cubed. This is what a general element of P3 looks like. And then we know that the elements of W are the ones that satisfy P prime of 1 is equal to P of 3, and so we can expand out that equation. So to do that, we'll first calculate the derivative of P, which is a1 plus 2a2t plus 3a3t squared. And then if we plug in t equals 1, we get P prime of 1 is a1 plus 2a2 plus 3a3. And then we're going to set this equal to P of 3, which is a naught plus 3a1 plus 9a2 plus 27a3. And so when we set these two things equal to each other, we get an equation that just involves a naught, a1, a2, and a3. We can move all the terms to one side. And when we do that, we get the equation a naught plus 2a1 plus 7a2 plus 24a3 is equal to 0. And this is actually a homogeneous equation in those four variables. And so in this case, what you would do is you would just treat a1, a2, and a3 as free variables, and then solve for a naught. But in general, you might have more than one equation, and so then you might have a system of equations, and then you would just solve that system of equations in the same way that we've been doing since the beginning of the semester. It's kind of interesting how ultimately everything in this class comes down to solving systems of equations. And really the thing that we've been learning in this class is that we've been enlarging the scope of problems which can be solved by solving systems of equations. And we're sort of seeing those systems of equations appearing in many different types of contexts. So anyway, in this problem, we're treating a1, a2, and a3 as free variables. And you could set them equal to parameters if you want, but you should avoid the letter t because the letter t is already in use as the variable for the polynomial. This is just one of those things you have to worry about when you're doing math that involves a lot of different letters. I'm just going to leave a1, a2, and a3 as they are, but just understand that those are parameters now. So then you can solve for a naught and get that it's minus 2a1, minus 7a2, minus 24a3, and we can plug this back into the formula for P of t. And then, remember how when you're solving systems of equations involving vectors, there's this step at the end where you can separate the different terms that are times each of the free variables? You can do that here at the level of polynomials. So there's some stuff that's times a1, plus some stuff that's times a2, and plus some other stuff that's times a3. And since a1, a2, and a3 can be anything, this is expressing the solution for P of t as a linear combination of three different polynomials. And those three polynomials give you a basis for W. So this calculation should feel very similar to what we were doing when we were solving for kernels, for example. But instead of working with vectors, we're working with polynomials. But otherwise, the calculations are basically the same and the steps are basically the same. And then finally, because there are three things in the basis, that means that W is three-dimensional. And intuitively, having W be three-dimensional sort of makes sense, because you're starting with the four-dimensional space P3, and then W is defined just by this one equation, P prime of 1 is equal to P of 3. And so that one equation should take away 1 degree of freedom, which would lower the dimension by 1, so you'd have a three-dimensional subspace. And in general, this is what you would expect to happen, that each equation would take away 1 degree of freedom and lower the dimension by 1. Except there's a possibility that there could be some redundancy in the equations or things like that. And that's really what linear algebra allows us to answer. You go through the process of solving and you can actually see how many degrees of freedom there are. And in this case, there were 3.